Hi everyone, so here we're finally seeing in this video how to pattern with t-SPL and DLS, so with the laser, on a bilayer lift-off stack. In the previous videos we have seen how to fabricate the BLO sample. In this case we have 30 nanometers of PPA on top of 100 nanometers of PMMAMA. Here we can see the laser efficiency, which will be also useful to remember later because it's not very high. So when we have a low laser efficiency, we may have to increase the laser power or the pixel time for the laser. So let's first start with the t-SPL patterning. So when we pattern on a BLO sample, as we mentioned in the previous videos, we want to make sure to open the wet development mask, which is PPA. So in this case, we have 30 nanometers of PPA. Therefore, we want to pattern deeper than these 30 nanometers. So I set here as target depth 35 nanometers so that I'm sure that there will be opening the PPA for the the PMMA, MA for the development process. Another thing to mention, so which are the designs that are quite useful, especially when testing the bilayer lift-off process, for testing the resolution of the lift-off process? Well, one example is this wheel, because as mentioned in the previous videos, one limitation of the BLO is the merging of the features when the spacing becomes too little and the isotropic process of the wet development will start causing the merging of our features. So in this case, we see that the features become progressively closer and closer. So at some point, we will see that the features will indeed merge. So of course, this will not really be achievable because we have 100 nanometers of PMMA. So this 100 nanometers of spacing will not really be achieved after the development process. So this is one design that we can use. So let's import it. I'm using a standard pixel size and the depth of 35 nanometers. That's mostly what's important. Maybe let's remove the scaling and let's have a standard dimension. Okay, so I place my design here. And I can start the patterning, maybe with a lower temperature and say a feedback, Kalman feedback. I still haven't tested any patterning, so let's see the feedback in action. Another thing to keep in mind when patterning with t-SPL on a bilayer lift-off sample is always better to pattern deeper than what we aim for than shallower, because if we pattern deeper, we're still able to open the PPA mask for the development process. But if we pattern too shallow, well, this may be a problem because we may not expose the PMMAMA underlayer or PMGI in case you use PMGI. So just keep this in mind. Here I just put a fast scan correction to maybe have better flattening. So keep this in mind because this is a very important thing. So always, if you have to pattern deeper, is definitely better than shallower. Here we see that we're patterning quite well. So again, this is just a test, and I want to pattern some structures that I hope can also help you to test your bilayer lift-off process. So as also recommended in the previous videos, always try to also double check your wet development rate. So maybe spin coat some PMMAMA or PMGI and try to do the development process and measure with a nanofraser or with an AFM the thickness after this test for the etch rate. Here we can see a design which can be quite useful to measure the resolution of the process. Another design that we can use is, which is by the way in the geometries which come with the nanofraser software, this undercut test. What can we see here? Well, we can see that we're basically patterning the dark area. So because of the formation of the undercuts, then we have a limited feature density. So we will see that these features will merge. This will merge. At some point, we will see that these windows are going to survive the development process. More specifically, we expect maybe with an overdevelopment of 50% and a PMMAMA thickness of 100 nanometers, that features of around 200 nanometers, 250 nanometer spacing will survive. So here we have 17.2, and the spacing here is a little bit more than 200 nanometers. So this, for example, should survive, while these lines, not really, because they are too thin. But maybe let's scale a little bit this design. We can put a scaling factor of 1.6 just to make it a little bit larger here, because we want to make sure to see at least some of these windows surviving. This will give us an idea of the density of the features that we can achieve. So for example, if this specific pattern survives, here we have a spacing of the feature of 0.8 to 0.15, so around 350 nanometers. So if this survives, it means we can successfully transfer features which are separated from one another by 350 nanometers. So even by optical microscope investigation, you should have useful data for the resolution of your bilayer Lift-Off process. So let's also add this to the layout. You can also check that the previous design was patterned nicely. Okay, we're not aiming for the high resolution. This is just a test to also give you some recommendations and good design that you can try to pattern in order to have a good testing for the BLO. And in general, we should also remember that the bilayer Lift-Off process cannot really achieve resolutions below 100 nanometers, except from very specific cases. So with PPA bridges that can act as shadow masks, but for very, very small structures like bow ties, antennas, so let's just maybe forget that for a moment, but let's remember that 100 nanometers pretty much which we can achieve as highest resolution with bilayer Lift-Off. So aiming for 20 nanometers resolution is in the end a little bit silly because it's not achievable by a wet development process. Here we see that we're patterning this design, which we can find later. Another advantage of the nanofraser for this kind of process is that we do a closed loop lithography. So now we're already seeing how our lithography looks like. But most importantly, we can also check after the development the depth of this structure. So if in this case we had 30 nanometers of PPA and then around 100 nanometers of PMMAMA. So if after the development we check again these structures and we see a total depth of 130 nanometers, it means that the development process was in the end successful. So one thing that's quite useful of using the nanofraser. So while this pattern is being patterned, we can also mention a few things about the patterning with the laser, or also maybe importing some other possible designs with t-SPL. Maybe one last design that we can pattern is an array of pillar. Sorry, in this case, it's an array of holes, my bad. And here we have a separation of 300 nanometers, so this should be transferred. Maybe we can try to pattern this one and another one with a smaller spacing, and then check with the nanofraser if this survived the development. So here we can see in the meantime that our pattern was not very good. In the end, for these first lines, we don't really care that much because we know already for sure that they will not survive the development process because the undercuts will cause a merging here. So what's important is that the next fields are going to look better. So indeed here it looks better, so this is what we want. Here maybe the depth is not so great. We can give a little boost in temperature. But so far this is looking good. So let's wait until this is done. And in the meantime, I would like also to make some consideration about the laser patterning, because after this we will see together some patterning with DLS on the bilayer off stack. What's important for a successful transfer of a DLS lithography step is that we pattern deep enough to open the PPA mask, but also we cannot pattern too deep or use a laser power that's too high, because this may cause some cross-linking of the polymer, which will then make the development process fail. So what we have in our nanofraser software is also a laser dose array test. So we would like to run this test maybe with a slightly optimized window of power in order to see which is a laser power which gives us a good depth of patterning, and then use this power to pattern the other fields in the areas that actually matter for the bilayer lift-off process. So we will pattern all these squares, and then we can use the nanofraser to read, let's say, this specific square, and we want to see the depth of the square. If it's around 35, 40 nanometers, that's good enough for the actual DLS patterning. So this is the approach that we typically use to optimize the DLS power and also pixel size for the development of the bilayer TOF sample. In the meantime, we see that here we are progressing quite well. It's going to take some time. In the meantime, I try to give you some hopefully useful information for your processes. So in this case, let's see the specific features. Here we have a separation of this one here. So here we have a separation of around 350, 400 nanometers. So in this case, we expect after the development process to see these windows surviving. What about the one below? So this one's here. Let's check. Here we have, on the other hand, around 100, 200 nanometers spacing. So these features may survive, may not, and this information will be useful to understand the resolution of our process. I will try to overdevelop by 50%, so I will target 150 nanometers of PMMAMA thickness removed. So here we see the last lines. Yeah, and the pattern is looking good, and it's not a high resolution patterning, so it's quite easy for the nanophaser to perform these last squares. As soon as this is completed, we can maybe start a quick hole patterns, and then we will perform a laser patterning, and then we close the video. One thing that's also good to keep in mind when we pattern with a nanophaser that has a DLS, we can easily make some markers. As you may have seen in this area, I made an arrow with the DLS. So whenever you have to find again the structures, well, these are clearly visible with the optical microscope, but in order to even facilitate this process, making an arrow that's much larger with the laser only takes a few minutes. So it's quite a useful tool to have also for this specific cases. Here we have really the last lines. Okay, seems good. Let's quickly import this design. depth of 35. So we can start this, and also have one with maybe smaller spacing. In this case we have a little bit less than 200. Let's even try to push it more. Let's put 0.7 maybe. You see that also we have distortions of these holes as expected. Here we have 140 nanometer separation, so this should not transfer. But it's always good to check, because in some cases, if the development is not so much overdeveloping, this can still sometimes survive. So also check in the meantime how this patterning is going. It's looking okay so far. We don't really need to finish the whole array. Once I see that we have holes with good enough depth, like here, I will say let's just wait to finish this other line. And then we can stop this pattern. Add this other one to the layout. And do a few other dots. So similarly here, we can stop it after we see that some dots have a good enough depth. Pattern here is even faster, so it's going to be a larger array of dots. Larger in terms of numbers of dots. Okay, let's stop it here maybe. Seems good enough. So far we have patterned these two structures to test the resolution of the development process. Now I just want to quickly show you. In the meantime, let's also see that I made this arrow as a marker, so quite large. Should be able to see it quite nicely with the optical microscope. Now I just want to quickly show you how to approach the patterning with the laser. So in the laser config here, you find the optional tools. The laser does array test. So let's say I want to pattern with the nanophaser from a laser power start of 100 nanometers to maybe 275. Actually, let's say 75 with a step of 50. And I want to use a pixel size stop at 300. Okay, this is just a simple array. It should take 7 minutes, maybe. Let's reduce it even more. Okay, it's going to be a smaller array because I just want to show you the concept. right? So you can make a larger array if you want to have a larger window of parameters for pixel sizes and for power. You can also find more details about the laser dose array test in the training videos, in the laser configuration videos. So we can press start and see the patterning. So we see that with this power, we're not really able to write. It's also expected because the writing efficiency on this specific stack is very low. So we calculated here that it's, yes, almost the minimum. So we expect to write only for high values of power. So here we're still not writing. We may, in case we don't write with any power in the power window selected here, we could increase the pixel time or reduce the pixel size, both in X and in Y. So you see that here we don't see really any writing, which also shows, I would say, the usefulness of the test, because and if we don't know which power to use, it's good to have an idea at some point of what can and what cannot write effectively. And we see that finally we start writing one square. As we increase on the right, basically we increase the pixel size. So as we increase the pixel size, it becomes less efficient to write with the laser. So here we see that at, I think, 225 milliwatt. So this one was able to write with a pixel size of 100 and 100. So once this is done, let's say we can check this square. We go to read arbitrary mode. And we can check the depth. Maybe increase the depth to -70, just in case we have a pattern quite deep. And now we can read this area. So ideally we will target around 40 nanometers, 35 nanometers depth with the laser. Of course, we always have to double check depth. Maybe we also add the thermal conductance correction to avoid some ghost images. Here we see that we're patterning quite deep, so we may need some further optimization. This can still transfer, but we may cause some cross-linking. And for this reason, I would say it's better to find another power window, maybe between these two values of power, to pattern not so deep. So if we would like to do another test, maybe we can put here 150 to say 225 with laser type of even 10 should do. And here we can put 175, and the pixel start, we can also just do a line to make it very fast. So in this case, we should see maybe a better when we start writing, and when we start increasing also the depth of writing. But anyway, this is kind of the approach that you should use in order to optimize the DLS for your bilayer lift-off process. And can maybe quickly see how this goes, and then we can close the video. So it's quite a long video. I try to explain how to pattern with both t-SPL and bilayer lift-off on a DLS on a bilayer lift-off sample. So it's quite a lot of information. I hope that this will help you in being successful with your bilayer lift-off patterning, and see you in the next videos. So yeah, as we see here, we finally start to write at the third square. Third was 205, so the window is definitely quite limited. We can also try to play a little bit more with the pixel size. So yes, that's it. Thank you for watching, and see you in the next videos of this bilayer lift-off set.